Mid-February 1943, near Sidi Bou Zid, Tunisia. The captured M4A1 Sherman eased to a halt in the pale desert sand, its U.S. star still faintly visible beneath a hastily brushed-on Balkenkreuz. Officers from Schwer Panzerabteilung 501 clustered around the prize, notebooks open, voices low with professional curiosity. This single American tank, seized intact and still fully functional during the fighting around Sidi Bou Zid, was about to unsettle German engineering confidence in a way that would ripple through their design bureaus for the rest of the war. The arithmetic of armored warfare was being redrawn, not by thicker armor or bigger guns, but by something the Germans had never truly prioritized: an automotive system that simply refused to quit. Its name was stenciled on the hull: War Daddy 2, Serial USA 3067641, built by Lima Locomotive Works, assigned to Company G, 1st Armored Regiment, 1st Armored Division. German reconnaissance personnel drove this Sherman roughly 350 kilometers across North African terrain to the port of Sfax, a 4.5-day trek. With every kilometer, the tank exposed assumptions German engineers had long held about American industry and found them wanting. The engine did not overheat. The transmission didn't falter. The final drives delivered steady output. German crews, used to frequent mechanical halts even on modest moves, watched with growing discomfort as this enemy machine just worked through heat, sand, and undulating ground that would have sidelined their own vehicles. At Sfax, War Daddy 2 was hoisted aboard a ship bound for Germany. The Army Weapons Office issued precise instructions. The vehicle must arrive at the Kummersdorf test facility intact and in running condition. German intelligence had pieced together sketchy reports about U.S. tank production, but touching the steel and hearing the engine changed numbers on paper into a reality that could not be denied. The Sherman embodied mass manufacturing at a scale Germany could not replicate, built on automotive design principles the Reich had never mastered. As the ship plowed north across the Mediterranean, Wehrmacht engineers drafted test plans to confront truths they had been reluctant to accept, both about their own constraints and about what American factories could produce. Spring 1943, Kummersdorf, Proving Ground, Brandenburg, Germany. War Daddy 2 rolled off a rail car wearing a new identity, a German test designation with the registration WH058941. Armor thicknesses and angles were already chalked across the hull and turret, neat stencils mapping every surface for analysis. Kummersdorf, 25 kilometers south of Berlin, served as the primary venue for evaluating German and captured equipment alike. Here, meticulous specialists gauged track tension, logged transmission efficiency, and dissected components with clinical thoroughness, producing dense technical reports on everything they touched. The Sherman was about to endure the most exhaustive automotive scrutiny German engineering could muster. The initial inspection brought together experts from multiple branches. They photographed details from every angle, measured tolerances with micrometers, and studied manufacturing techniques that seemed almost shockingly simple compared to German methods. The transmission immediately attracted the powertrain team's attention. While German tanks favored straight-cut gears, demanding tight tolerances and vigilant maintenance, the Sherman used herringbone-cut gear sets that spread loads across multiple teeth at once. Standardized in U.S. automotive production since the 1930s, this approach delivered excellent durability without obsession over precision machining. German designers had long judged such gears too challenging for their industrial base to produce in volume. Americans had been turning them out by the thousands. Tests began with straightforward automotive trials designed to probe every system under controlled stress. Crews drove War Daddy 2 through a series of obstacles mimicking field conditions, tracking fuel burn, monitoring engine temperatures, and recording how the transmission behaved under different loads and surfaces. After each cycle, they pulled parts apart to study wear patterns, looking for hot spots, lubrication failures, and design weak points. The findings undercut cherished assumptions within German doctrine about the supposed trade-offs between capability and reliability. The Sherman performed competently across the board and excelled in the one area where German tanks consistently stumbled, staying in action without constant mechanical nursing. The powertrain study highlighted a philosophical divide. The Sherman carried a 5-speed gearbox with one reverse, its second through fifth gears synchronized to eliminate the need for double clutching in routine driving. As a result, it handled almost like a civilian car, requiring far less specialized training for drivers. German tankers, in contrast, spent significant time mastering double clutch technique and throttle finesse just to avoid damaging their boxes. The American design assumed ordinary soldiers with basic automotive experience would drive. The German approach assumed access to expert operators. The Sherman's Continental R975 radial in this particular tank showed remarkable resilience across varying conditions. Test logs noted that power output remained steady across temperature bands that typically pushed German engines into overheating and power fade. The cooling system, despite its straightforward layout, was robust. Air filtration handled fine desert dust without the frequent clogging that plagued German vehicles in North Africa. Everywhere the engineers looked, they saw a design language aimed at practical functionality rather than theoretical perfection. June 6–7, 1943, Hillersleben Artillery Range. Reichsminister Albert Speer arrived to oversee a major armaments conference that brought together senior Wehrmacht officers and industry leaders. The program featured hill climb comparisons with both domestic and captured vehicles. War Daddy 2 stood beside Germany's newest creations, including a Panther AOSF, D straight from production, and a Ferdinand tank destroyer showcasing the latest in German armored engineering. Speer, directly responsible for armaments output and accountable to Hitler, needed a clear sense of what America could deliver and how German machines stacked up. What followed offered answers neither he nor the design offices were eager to hear. The Sherman took the slope smoothly, its 5-speed gearbox, synchro from second on, snicking cleanly through ratios while the engine pulled with reliable vigor. The driver's confidence came through in the steady pace and calm corrections, an ease of operation that would become synonymous with the type. The Panther followed. Its 700-horsepower Maybach HL230 gave it the thrust to keep up, but only just, and with appreciably more difficulty. The Ferdinand, a 65-ton colossus with an advanced electric transmission, stalled partway up. Speer watched as recovery teams wrestled with the immobilized vehicle, a very public embarrassment in front of brass and industry VIPs. In his memoirs, written years later, Speer described what he saw in the field, notably during an October 1944 inspection tour of Italy. Reports on the Sherman's cross-country mobility, he noted, were impressively positive. The tank had scaled slopes German specialists had written off as impassable. He attributed this in part to a high power-to-weight ratio that gave it off-road performance on flat terrain, superior to that of German machines, a view echoed by the 26th Panzer Division. Speer's assessments carried real weight within Wehrmacht circles. A carefully worded piece in Das Reich on June 27, 1943, praised the Sherman as one of the special achievements of North American laboratories and a commendable product of the U.S. steel industry. The article highlighted its serial production ethos and the apparent fulfillment of what it called the almost arrogant demands of the U.S. auto industry. It even acknowledged the gyro-stabilized gun as the first attempt of its kind anywhere, a nod to American innovation. While the public message avoided defeatism, it masked the growing alarm inside German technical offices. American tanks weren't merely adequate. They were engineered from the start for sustained operations in the field. Back at Kummersdorf, the test program rolled on through summer into autumn 1943. Engineers pushed the Sherman's range in extended runs, logging distances beyond 2,000 kilometers before major service, roughly quadruple what early Panthers managed in real-world conditions. Drivetrain efficiency measured above any German counterpart, with power losses through the transmission and final drives lower than comparable domestic systems. The synchronized manual gearbox made shifting simple and forgiving, sidestepping the double clutch and rev-matching rituals German transmissions demanded. Final drives presented another hard lesson. Panther units used final drive arrangements derived from the Tiger's design, straight-cut gear sets in housings that didn't stand up under a 45-ton vehicle's loads. Reports from North Africa and the Eastern Front told of final drive failures that left Panthers abandoned after surprisingly short movements, sometimes under 100 kilometers. The Sherman's final drives, built around the same herringbone principles as the transmission, almost never failed, even under continuous combat stresses that shredded German components. Decades later, restorers would open up Sherman final drives and find them requiring little to no work after long storage, proof that factory design margins had been generous. By late 1943, Kummersdorf's files were thick with data, enough to support comprehensive internal briefs circulated among Wehrmacht technical staffs and armaments officials. The picture was sobering. The Sherman revealed a level of automotive maturity in American industry that Germany lacked, despite its theoretical sophistication. Mass production enabled tolerances that German precision culture would have labeled crude. Yet those looser tolerances produced vehicles that ran better in the real world. Interchangeability meant field repairs could be performed with basic tools by mechanics with ordinary skills. German machines, by contrast, often required near-factory-grade precision and specialized tools to put right. The American philosophy prioritized keeping vehicles available to fight. The German aim of achieving impressive theoretical peaks often led to systems that couldn't sustain those numbers in combat. Internal analyses didn't stop at technical drawings. They also reflected on the industrial ecosystems that produced these results. The U.S. had decades of civilian automotive experience behind it and widespread car ownership across social classes before the war. Germany did not. Private automobiles were far rarer, and the much-trumpeted Volkswagen initiative had delivered fewer than 1,000 civilian cars by 1939. That gap in civilian motor culture translated directly into different design outlooks. Americans built tanks that a mechanic with general automotive knowledge could keep going with familiar tools. Germans built tanks that assumed expert specialists would always be on hand. As frontline reports piled up through late 1943 and early 1944, the comparison became unavoidable. Panthers had to be used within strict limits to avoid killing their own drivetrains. Drivers were warned to minimize gear changes because repeated shifting could damage the box. Third gear in particular broke so frequently that manuals and instructions stressed, avoiding it unless absolutely necessary. Reversing while turning was forbidden, as it would wreck the transmission. Pivot turns were discouraged, unless track resistance was roughly equal on both sides. Even small stones and debris could jam the drive sprocket, leading to hours of maintenance. All of this was happening despite the Panther being built in dedicated facilities by skilled workers using the best materials Germany could marshal. The Sherman's lineage was different. It bore the imprint of engineers at General Motors, Ford, and Chrysler, who applied the mass production logic they had refined over decades. Where they could, they used commercial components and leveraged existing supply chains. Multiple firms, including Caterpillar Tractor, Buick, and Ford, built transmissions to the same spec, and parts were truly interchangeable. You could mix components from different manufacturers without fitting or handwork. That level of standardization, routine in Detroit, remained more aspiration than reality in German tank production, where each factory's subtle variations often sabotaged interchangeability. More captured Shermans reached Kummersdorf in 1943 and 1944, taken from British formations in Italy and from Soviet forces on the Eastern Front. Each vehicle went through the same regimen, building a broad database across variants and batches. The British conversions with the 17-pounder, known as Fireflies, drew special interest. They addressed the Sherman's main weakness, firepower, by fitting a much larger gun. German teams noted how the Sherman's ample turret ring allowed the upgunned installation with limited structural changes. That hinted at growth space baked into the original design, something German engineers had not allowed themselves on the Panther, which had been rushed into production against the T-34 and lacked room for substantial armament upgrades without major redesigns. Kummersdorf expanded the program to reliability trials that better simulated combat. Crews drove Shermans for hundreds of cross-country kilometers, logging every hiccup, repair, and failure. Those logs were compared with field reports from Panther and Tiger units fighting in Russia and Italy. The statistics told a blunt story. Panther operational readiness averaged under 40% for most of 1943, with some units dipping to a disastrous 20–25%. There were times when a battalion had fewer than 1 in 5 tanks truly combat-capable. By contrast, Sherman units consistently kept a much higher share of vehicles running. Specific cases were damning. In July 1943 at Kursk, Panthers managed only 16% readiness, with mechanical attrition outstripping combat losses. By December 1943, that number crept up to 37%. February 1944 remained at 37, April reached 50, and May finally touched 78. Even then, the best Panther availability never matched what Shermans had delivered from the start. By the close of 1943, the pattern was plain to anyone reading the raw data. Sherman diesel engines could run past 3,000 kilometers with proper maintenance. Improved Panther engines, according to March 1944 reports, achieved service lives of 700 to 1,000 kilometers and were touted as an improvement, still roughly a third of what Sherman diesels managed. The Sherman's transmissions asked little between overhauls, their synchronized gears protecting the machinery from driver mistakes. Panther boxes demanded frequent attention, with third-gear failures so common that drivers learned to jump from second to fourth. Sherman final drives stayed intact under duress that often destroyed Panther units within 100 to 200 kilometers. Field experience from German formations using captured Shermans reinforced the test ground conclusions. Hard-pressed units, hungry for anything reliable, eagerly took intact American tanks and employed them with minimal fuss. Unlike Soviet T-34s, which Germans usually modified before committing to battle, Shermans often entered service as is. No sweeping changes were necessary because nothing fundamental needed fixing. Tankers who had endured repeated breakdowns in their own mounts noted the Sherman's dependability in letters and after-action reports. Panzer regiments remarked that Sherman crews could concentrate on tactics and gunnery, whereas Panther and Tiger crews had to worry first about making it to the fight and then about surviving the mission without mechanical immobilization. One striking example came during Operation Nordwind. In January 1945, at Herlesheim, the 10th SS Panzer Division overran and captured a dozen M4A3 Shermans from the U.S. 43rd Tank Battalion, abandoned intact under pressure. The Germans formed these into the 13th Company of the 10th SS Panzer Regiment. using them in combat through the war's last months. They served as reconnaissance elements and mobile reserves, jobs that demanded long movement without the luxury of frequent maintenance halts. Commanders trusted them because Kummersdorf's findings had been borne out at the front. American tanks would do what they were asked, when they were asked. In the end, reliability mattered more than paper armor thickness or theoretical firepower. A Sherman that reached the line with its gun ready was infinitely more valuable than a Panther with superior ballistics stuck 20 kilometers short with a broken final drive. In January 1944, as Wehrmacht units fell back across multiple fronts and more captured materiel flowed in, the Kummersdorf program broadened further. Engineers examined the M4A1 with the Continental R975 radial, cataloging its behavior relative to other models. They tested the M4A2 with its twin GM6046 diesel, noting better fuel economy and a different character under load. They ran the M4A3 with the Ford GAA V8, widely viewed by American crews as the best of the Sherman power plants. Across the board, the same core traits stood out: outstanding automotive reliability rooted in sound engineering and consistent manufacturing. The uniformity across variants impressed German specialists accustomed to noticeable quality swings between production batches and makers, where their own supply chain often produced small but consequential deviations. The American system delivered parts and vehicles that fit, worked, and kept working, regardless of who stamped the serial number.